Taking the absolute value of a number is a relatively simple task. If the number is negative, you just make it positive, and if the number is already positive, you just leave it as it is. But what if we try to do this process in reverse? What if we know that the absolute value of a number is 7, and we want to know what the original number was? Well, this is the situation that arises when solving absolute value equations. So without further ado, let's solve some absolute value equations. Here are 3 different equations that contain the absolute value. And while they might all look quite similar to each other, there are some important differences between them that we should go over. So let's start with the first equation. This equation is asking the question, the absolute value of what number equals 7? Based on the definition of the absolute value, another way we could phrase that question is, what number is 7 units away from 0? Well, the answer to these questions might seem rather obvious to some of you. It's 7, right? Well, in a sense, yes. The absolute value of 7 is 7, so 7 is a perfectly valid value for A. However, if we look at our number line, you might notice that we only moved 7 units to the right. But couldn't we also move 7 units to the left? Yes, we could. And when we move 7 units in that direction, we see that -7 is also 7 units away from 0. So we end up in a situation that might be new territory for some of you. There are 2 answers to this equation. A could be 7, or it could also be -7. And so we write our answer this way. Notice that we didn't say that A is 7 and -7, because A can't be both numbers at the same time. Instead, we used the word or to indicate that the answer is one number or the other. Now for our next problem. This equation is asking the absolute value of what number equals -3. Based on our last problem, you might be thinking that the answer could be 3 or -3, and that would be a reasonable first guess. But if we take the absolute value of either of those numbers, we get an answer of +3, not -3. So what's going on with this problem? Well, if we think back to the definition of the absolute value, it was the distance of a number from 0. Can our distance from 0 ever be -3? No. Distances need to be positive or 0, so this is an impossible situation. And thus, this equation has no solution. The first equation that we solved had 2 solutions, but then the next equation that we looked at didn't have any solutions. So how many solutions do you think this equation will have? Well, it turns out to just have one solution. When the absolute value of a number is equal to 0, that means that the number is 0 units away from 0. And the only number that satisfies that condition is 0. Now that we've gone over the basic types of absolute value equations, let's add some extra steps to our equations and see how that goes. We'll start with an example that looks similar to one of the problems that we did on the last screen. And there may be an answer here that jumps out at you. 4. If we plug that into our equation, we can quickly see that 4 is indeed a solution. So we have an answer to our equation. But absolute value equations can have multiple answers, so we're not done yet. In fact, if we were to make another guess at a solution to this equation, -4 might be a good candidate, since we've already seen an example of an absolute value equation where the answers were just the positive and negative versions of the same number. So let's try out -4. -4 plus 3 is -1, and the absolute value of that is +1. That didn't work out. So how are we going to find out if there are any other solutions to this equation? Well, let's go back to our original equation, but instead of guessing and checking, we're going to try boxing this time. Since x plus 3 is happening inside the absolute value bars, we can think of that expression as a single unit and draw a box around it. Then, we can see that the absolute value of the box is equal to 7. But that's the same equation that we solved earlier. When the absolute value of a was equal to 7, we deduced that a could be 7 or negative 7. So the same thing applies to our box. It can be equal to 7 or negative 7. Now that we have these two equations, we need to think back to what the box actually represents. It stands for the expression x plus 3. So let's replace the boxes with x plus 3. Once we do that, we just have a couple basic linear equations to solve. In this first equation, we subtract 3 from both sides to find that x can be equal to 4, which is the solution that we guessed at earlier. Then, in our second equation, we subtract 3 from both sides to find that x can also be negative 10. Just to be safe, we'll double check that negative 10 works in our original equation. And it does. So that gives us two solutions to the equation, 4 and negative 10. Something to note about our solutions is that even though they weren't just positive and negative versions of the same number, there was still one positive solution and one negative solution. This will happen regularly with absolute value equations, but is it always the case when there are two solutions? Let's check out another problem to test out this question. In this problem, we're going to start by boxing right away. We'll box everything that's inside the absolute value to see that the absolute value of the box is equal to 1. This means that the box can either be 1 or negative 1. So let's write out those two equations. Then, we'll replace those boxes with the expressions that they represent. This gives us two equations to solve. In each equation, we could draw another box around the 3y, and you're more than welcome to try that out on your own. But at this point in the video, we'll skip that step and solve the equations using standard strategies. This gets us solutions of 3 and 7/3. So earlier, we asked ourselves if absolute value equations with two solutions always had a positive solution and a negative solution. This problem that we just solved definitively answers that question, and the answer is no. Our equation had two solutions, but they were both positive solutions. Similarly, we could have a problem with two solutions that are both negative. So now that we've answered that question, let's look at some more examples of absolute value equations. This first problem differs from the last problem we did because the multiplication and subtraction are happening outside the absolute value bars rather than inside of them. In fact, we can initially ignore the absolute value portion of the equation by drawing a box around it. And once we rewrite the equation with a box, we can see that this remaining portion is just a linear equation. So we add 7 to both sides, and then divide both sides by 4 to see that the box is equal to 8. Then, we replace the box with the expression that the box represents, and we see that our two solutions are 8 and negative 8. In our next problem, we're going to start once again by drawing a box around the absolute value bars. Then, if we divide by 3.1 on both sides, we'll be able to isolate the box and move forward in the problem-solving process. Next, we can draw a box around the 1.4 minus b to see that the absolute value of the box is equal to 4. This means that the expression inside the box can either be 4 or negative 4. Then, we subtract 1.4 from both sides of both equations to see that negative v can either be 2.6 or negative 5.4, which means that v can be either negative 2.6 or positive 5.4. Now that we've solved several absolute value equations using the boxing method, let's reduce the amount of boxing on this screen. Instead of drawing a box around the absolute value portion of our next equation, let's just work through the first couple of steps with the understanding that we could draw a box there if necessary. Then, when we subtract 3 and divide by 5, we end up with this equation. Now, since the expression inside the absolute value bars has a bit of complexity, let's draw a box around that expression and analyze the equation from there. This gets us to the point where we should be asking ourselves, the absolute value of what number is -1/5? But wait, will the absolute value ever give us an answer that's negative? No. That means that it's impossible to find a solution to this equation, and we express that by saying that there is no solution. Let's follow that up with a problem that contains several fractions. Once again, we'll hold off on boxing until we get the absolute value isolated. But once we get to that step, we'll draw a box to see that the expression inside the absolute value bars can be either 1/2 or -1/2. From there, we'll need to do several more operations with fractions, but eventually we'll see that n is equal to 27/4 or 21/4. On our final screen of this section, let's try a couple more examples without any boxing this time. In this first equation, we start with a term of -4, which we can eliminate by adding 4 to both sides of the equation. Then, we can divide by 6 to get the absolute value portion of the equation on its own. At this point, we separate things into two equations, one equal to a positive value and one equal to a negative value, and solve from there. And next, we'll start by subtracting 2 from both sides, after which we'll multiply by 7 and add 1. This once again gets the absolute value portion of the equation on its own, but there's something special going on here. The absolute value is equal to 0. This means that the expression inside the absolute value bars must also be equal to 0, so we don't even need to split this problem into two equations. From there, we can subtract 3 from both sides and divide by -4 to see that q is equal to 3/4. In order to push our understanding of the absolute value a little bit further, let's take a look at a couple final equations that feature some advanced concepts. Although this equation may not look too different from what we've done before, the second set of absolute value bars will complicate matters a little. Notice that with the use of a box, though, we can abstract away the inner set of absolute value bars and just focus on the outer set. Rewriting the equation then shows us that the box is equal to either 1/3 or -1/3, and replacing the box with the expression it represents gives us the following equations. Next, we need to add 2 to both sides of both equations, and similarly, multiply both sides of both equations by 5. This brings us to the second set of absolute value bars, which means that we get to split our equations into two parts again. Once we do that, we can complete the final steps of all 4 equations to find our final answers. And while we could leave our answer as it is along the bottom of the screen, a more convenient notation here might be set notation, which allows us to concisely express that x is one of these 4 numbers. And finally, here's one last problem that also contains 2 sets of absolute value bars. However, instead of one set being inside the other, these 2 sets are separate from each other. And while there are several methods that we could use to solve this problem, we're going to use a method that emphasizes the formal definition of the absolute value. Recall that the absolute value of x is sometimes equal to x itself, and other times is equal to the negation of x. The same concept applies to the absolute value of any expression, like z plus 7 for example. The absolute value of z plus 7 is sometimes simply equal to z plus 7. But other times, that expression needs to be negated, and the output of the absolute value will be negative z plus 7, which simplifies to negative z minus 7. A similar process can be done for our other absolute value expression, and with some modifications, we can represent the entire right side of the equation in one of these two ways. Once we've established these conditions, there are 4 cases that can arise in this situation to potentially give us solutions to our equation. We could have the first option on the left side of the equation be equal to the first option on the right side of the equation. Or we could have the first option on the left be equal to the second option on the right. Similarly, we could have the second option on the left be equal to either the first or second option on the right. Altogether, this gives us 4 linear equations that we can solve to find our solutions. So let's go ahead and solve each of them. Once we have all 4 solutions, it would be reasonable to think that we're done with the problem now. Unfortunately, though, there's a small issue with the strategy that we chose to solve this problem. Sometimes we get answers that aren't actually solutions. So now we need to go through each solution and check it in the original equation. As we do this, you'll see that certain answers are actual solutions to our problem, while other answers are not. These answers that arose during the problem-solving process, but that were not actual solutions, are called extraneous solutions. So as you can see here, 2 of our apparent solutions were extraneous solutions, leaving us with only 2 actual solutions to our equation. That concludes this video on solving absolute value equations. Hope you learned something new, and thanks for watching.